All right, so we're going to try and do this in one take. I have kind of a wobbly camera in front of me, pen and paper. The camera kind of autofocuses and I can't really turn it off for some reason, so we're going to do the best we can. So tonight we are going to talk about sorting. If you recall, um, last lecture we talked about vectors, which are basically really fancy dynamic arrays. So if you hear me say array instead of vector tonight, I'm really referring to any sort of structure with a random access operation, such as a square bracket operation or a dot at operation. And this is important because having random access is really useful when you're trying to sort things for most algorithms. There are plenty of modifications you can make to some algorithms to work on lists or sequential access, but typically when you're talking about it or you see it, you're dealing with random access. And the reason I'm talking about it after vectors is because random access on a vector is in constant time, which means it is the most efficient, which means these sorting algorithms also run most efficiently on vectors and or arrays. So when we talk about sorting, we mean sorting such as taking a scrambled up array such as 1, 3, 6, 2, 5, and putting it into proper ordered sequence, such as 1, 2, 3, 5, 6. And there are tons of algorithms that do that. I am so sorry about the really awkward autofocusing. Um, we've talked about algorithms a little bit before in terms of sorting. I gave some resources last week about them. By the way, make sure you do you look through the other resources because they'll be kind of related to this. They'll be kind of related to what we're talking about on Thursday. Um, we've talked about other sorting algorithms. By that I mean you guys had to research and implement one. We're going to talk about a couple today. We're going to talk about different strategies for sorting. We're going to talk about how these can be modified a little bit for different kinds of sorts. Because while we're going to refer to this as properly sorted, there may be other things that would be considered properly sorted depending on the different context you're using a sorting algorithm in. For example, you may want descending order. So in this case, it would be 6, 5, 3, 2, 1. In some cases, you may want all of the even numbers to be sorted before all of the odd numbers, which are sorted afterwards. Um, so let's just jump into the different algorithms then. And before we do that, let me tell you about we have different strategies that are used with sorting algorithms. So different strategies are stuff such as iteration over the algorithm, or perhaps division division of the array. And I mean iteration over the array as well, not iteration of the algorithm. Um, and usually there's some sort of comparison that's done. And this comparison is used to determine which goes before what. So in most sorts, we usually say A greater than B, or B less than A, or in the reverse. Um, and really, that comparison is where you change what kind of sort it is in terms of the order that you are attempting to create. The algorithm is what determines what kind of sort it actually is. So merge sort versus bubble sort versus selection sort. Um, but typically this comparison is where you change how things come ordered. And finally, we have some sort of operation. And this operation is typically what is used to actually perform the sorting operation. So sometimes we have a swap operation. Sometimes we have a insertion, a merge. There's all kinds of different operations here. And so tonight I'm going to try and talk about two different sorts. We're going to talk, or two different comparison sorts, I should say. And we're going to talk about selection sort, and we're going to talk about merge sort. And we're going to talk about one non-comparison sort called bucket sort. And this one's really interesting because it can be incredibly efficient or incredibly inefficient depending on parameters you give it. And I feel it's important to also show that other than these typical comparison-based sorting algorithms, you can also have great results using different approaches. All right, so let's first start with selection sort. Now, selection sort is a sorting algorithm where you basically select the smallest item in the array, you iterate over the array. Well, first you iterate over the items in the array, and then from that first item, you iterate over all the rest of the items again. So say we have 5, 3, 6, 1, 2. I'm being very original with these numbers if you can't tell. We would start, say, at 5, which means we would work off of this part, and we would set our min to 5. And the min is just so we know what's the smallest, or we're going to set the min to 0 actually. Apologies. And basically what we do is we take the index of where the smallest number we know of is, and then we iterate over this part that I drew over slightly later. And then we check if this index has a smaller number than here. And if so, we replace that index. So 1. Here it's not any bigger. Here, so we're 0, 1, 2, 3. We have 1, and then here it's not. And so what we do after that iteration is we swap the two. So we have 1 here, and we have a 5 here. And then we put 3, 6, 2, and it's in order like that. Next, we start here. We go on to this portion of the array, and so on and so forth. I think you get the idea from there. We would say min equals 1. We would keep checking here. We would see that 2, 3, 4 is the smallest one. That gets swapped. 1, 2, 6, 5, 3, and so on and so forth. And that's a pretty basic sorting algorithm. In fact, I'll even just write down some basic, it's not going to be like formal pseudocode you would see in a textbook, but it's sort of C-like so you can kind of understand it a little bit better. But you end up with something like for I equals 0, I less than n minus 1, I plus plus. And the reason we do n minus 1 is because by the time we're here, we don't need to go on any further. That should just be in place, right? So no big deal. Oh yeah, and we have to assume A equals the array. I'm just putting this for your guys' benefit. N equals size of A. So we have this for loop. We set our min to be I, which is the current item we're on. Pretty simple so far, right? Now we go for j equals 0, j less than n, or actually we want j equal to I plus 1, because that way we're not backtracking over any of this. J less than n, and then j plus plus. We check if a at I, which would be the current item, is, or a of j rather, apologies, is less than a of min. And if so, we set min equal to j. And then that loop will keep running. We'll have a min by this point, and this will be the actual min. And if min does not equal I, we do the swap. Pretty easy, right? And I believe a couple of you have already implemented this algorithm and still need to post your results on the Canvas thread later on tonight. Yeah, this is pretty simple. This is a fairly commonly used one. Now let's look at the complexity. So right here we're always going over basically n items, right? And so here the size of this changes every time, which we start at n minus 1, goes to n minus 2, all the way to 1, right? Which basically comes down to it being something like n minus 1 over 2 when you combine the two here. So this comes out here. So that basically comes out to n squared and some constants based on how long swaps may take, if swaps need to be done, etc., etc. So it's a little better than bubble sort in the regard that you're not swapping all the time. You're saving time on that. But it's still in a class of O of n squared because we're still essentially going over the array n squared times every time we're running this sort. So it's not the greatest, but the best case is the same as this case, which means we could actually argue for theta because we're consistent in that we are always going to be running that many times. Now let's talk about merge sort. And merge sort's a little more complicated because merge sort is also considered a recursive algorithm. I'm not going to show too much code on this. I'm not going to talk too much on the complexity on this because it is a little complicated. And we are going to get into the complexity of recursive algorithms when we talk about searching in a few weeks. But merge sort is a divide and conquer algorithm, which basically means we're dividing up the array into several pieces. We're performing an operation on those pieces, and then we're putting the pieces back together for one final result. And so the idea is that with a merge sort, you're going to break the array down into a smaller size. So let's go 6, 1, 3, 2, 4. We haven't used 4 yet. I bet it feels left out. And let's add one more, just for sake of a little bit of simplicity here. So we'll add 5. So 1 through 6. We'll have this array. And we'll keep splitting it up. And eventually we'll end up in everything being somewhat like that. So we have 6, 1, 3, 2, 4, 5. We'll have some empty array over here that we copy back to. And basically, what we do is we merge it back into bigger pieces. Based on, we take the bigger one, we put it on this side of the smaller one. So over here we would end up with 1, 6. Here we would end up with 2, 3. Here we would end up with 4, 5. And as we keep going down, you do comparison here, and then you sort of compare over here. And since that already works, we would have 1, 2, 6, and then 3 over here. We'd have to do comparisons across the way. Not too bad. 1, 2, 3, 6 on this side. And then 4 and 5 over here. And then we do the same comparisons across here. Then these get inserted over and then copied back. So merge sort works pretty well. It typically runs with two functions. It has the actual merge sort, and then it has a different sort of merge partition function, which takes a start and then the array. And then what merge sort does is it calls merge part on exactly half on each side. And then the merge part will also work in a similar way. It will pretty much keep breaking it up until it needs to do, or until it's at its base cases, and then it starts doing its swaps and then returning back that. That part keeps returning that, and it just keeps sort of snowballing. And if you look at the pseudocode on, say, Wikipedia, or I believe there's a version of it in the textbook as well, it'll show that it works recursively, and you end up with a final call to something like merge here at the end, which does the final merge. And merge sort and merge part are essentially the same functions. And so when we look at it from a complexity perspective, this is one of the best algorithms we have. It ends up taking the merge step itself takes theta n. When you're dividing up the array, that's constant time. But the actual merge part and then merge back together ends up being along, let me check my notes here real quick. Because I have this big proof up from a book. Yes, that's what I thought. Okay, so we end up in big O of n log n. And the log n comes from the recursive part. The way it runs, it only goes over each element log n times, or n log n times, because it has to go over each element, but the compare and swap only takes log n times. And by swap, I actually mean inserting. When you're doing this to insert this over here, it takes log n time, because we're only working on log n part of the full array. And now let's talk about non-comparison sorting. And by that I mean we are going to talk about bucket sort. So I want you guys to take a guess at what this might be before we actually talk about it, just in your head real quick. So I'll tell a story about this real quick because it's very relatable to my childhood. I used to collect Pokemon cards, and the way I would always sort them out to put in binders is by the set number, like the number in its set out of how many total in the set. And the way I would always sort them out is I would put all the ones that are below 10 in one pile. I'd put all the ones that are 10 to 20 in another pile, 21 to 30 in another pile. And it worked out really well because it was another sort of divide and conquer strategy to sorting them all out, putting them in the proper order. Now, bucket sort, if you couldn't guess from this story by now, is where we say we make n number of buckets, sort of like this. And then as we're going through the array, so as we're going to the array, if it's below a certain threshold relative to the buckets, it'll go into that bucket for sorting on that particular bucket. So for example, we would say this would be bucket 1, 2, 3, 4, 5 to 6. And we would put in 3 here. We would put 6 here. We would put 2 here, 1 here, 4 here, and 5 here. And then what happens is, well, in this case it's real easy. It's just a swap if need be. But you typically run either another sorting algorithm. Selection sort's actually really good for this in an optimization that I'll talk about in a moment. But you'll run another sorting algorithm on this or another bucket sort to expand it out further. So in this case, we would end up doing some other sort. We would get 1, 2, 3, 4, 5, 6, and then that all becomes one big array or vector. And then everything's in order. Pretty simple, right? And so the complexity on this really varies. It really varies. The complexity actually depends entirely on your parameter n. And I made that a big N, so when we're talking about complexity, I can still use little n for array size. And big N can be the argument we gave. I know that's probably not the best choice because we have two n's to talk about, and I'll try and discern them better, but on paper here, it should make a lot of sense. So in the worst case, you're going to look at something big O of n squared, for the sole reason that you're going to be running a selection sort or some other sort over all this while going over the entire array once already. It's not going to get worse than an O of n squared unless you choose a really bad sorting algorithm at this stage. Now, this algorithm can, in best case, get to big O of n. And how do you do that? For big O of n, you have to make enough buckets for each item. So for example, we have this array here, and we're going to say big N equals 6, which means we have a bucket for each item. And then we're just dropping 1 here, 2 here, 3, 4, 5, and 6, and then we have our array already made. And this is similar to a pigeonhole sorting algorithm, which you can look up on your own time. I highly recommend looking that one up because it's fairly similar to the bucket sort, but it's also kind of interesting to think about it, and the naming is kind of hilarious. But That's how you get O of n on a sort, but it also takes up a lot more memory. Now, another optimization you can make while keeping big N to a different size is selection sort over the entire thing after you divide the buckets up. So this is kind of a modified bucket sort, but it works really well because with selection sort, you're much more likely to, or the items that are going to be shifted are going to be much closer to the item that's smallest, meaning we cut down on the number of swaps dramatically, which is very good for time complexity's sake. So in this case, we have 2, 1, 3, 4, 5, and 6. Or 6 and 5, rather. And so we'd compare here, we'd have 1 swap, 2 swap, without going over the entire array, mind you, because all of the things that need to be swapped are already close together. This also depends on your n, but regardless of your n, this way makes, while taking up more space, is still more efficient than just a standard selection sort. Now, real quick, I want to talk about comparing the complexity of algorithms real quick. So I gave out a thing last week about the limit test. And if you don't remember, it's just a test that takes the complexity of two different algorithms. And when we have those two algorithms, we can check the limit of one function over the other. And depending which way it goes, it tells us a lot about the relationship of the two algorithms. So for example, let's take merge sorts, n log n. And let's take selection sort or bubble sort or your favorite simple sorting algorithms, n squared. So if we have the limit as n goes to infinity, not 8, we want infinity. And we take that of n log n over n squared. What does that result in? So n squared grows much faster than n log n, which means this is going to end up going to 0. And what that means is the top function grows much slower than the bottom function, which is literally what we said, but that also means that this is in a smaller time complexity than this. It means that while n log n is still considered part of n squared, it's a weak relation, which means n squared is not the absolute worst time that this is going to achieve. And that also means that this is, in fact, a more time-efficient function or space-efficient function, depending how you're looking at it. Regardless of what you're looking at, be it time complexity or space complexity, this will tell you which is in a more complex class. And if something is a member of a class, is the higher class really the best option or the best way to determine what big O is? So that's what I was going to talk to you guys about tonight. Let me know if you guys like this format to keep doing this on Tuesdays. If you want me to just keep giving you resources and have me shut up, just let me know. I appreciate all feedback, and I hope I can do this again for you guys.